Hi boys and girls. In the last presentations I told you about the coherent schemes of digital modulation like BPSK, QPSK, etc. Then we saw the binary phase shift keying, that's all, binary frequency shift keying, that's also another coherent scheme. Coherent scheme means whatever basis function that is used in the receiver transmitter that is available in the receiver in phase coherence. But there are other non-coherent schemes, one such is differential phase shift keying. It is rarely used anywhere, but it is included in your syllabus, so let me go to that presentation. So in this presentation you will learn the theory of differential phase shift keying, and then you will learn the block diagram of DPSK transmitter and receiver. And here this is a BPSK transmitter, DPSK transmitter. If you look here, it is basically a BPSK transmitter. If you look at here, this is a level shifter and a dot product. This is essentially a BPSK system, but the difference is that the bits, the bits to be transmitted, they don't directly go into this BPSK system. Instead, it goes to a logic circuit. So here, this goes into an XNOR circuit. This XNOR is nothing but a complement of a modulo to addition, and here this bit decay, this is delayed by one clock cycle or 1 TB, that is 1 bit period, and it comes here. So this BK is XNORed with DK minus 1, and effectively this DK goes into my BPSK system. Now suppose this BK is say this pattern, as an example, if this is 10011100001, and if the previous bit DK minus 1, let that be 1, then the bit pattern going into the BPSK modulator will be like this. This is my bit pattern BK, and this is my let the previous bit be DK minus 1 is 1, so that 1 XNOR 1 is a 1, and 1 XNOR 0 is a 0, 0 XNOR 0 is a 1, 1 XNOR 1 is a 1, likewise 1 XNOR 1, 1 XNOR 1, again 1 XNOR 0 is again 0, 0 XNOR 0 is a 1 because both are equal. So 1 XNOR 0 is a 0, 0 XNOR 1 is a 0. So the corresponding phases are, so here I give phase pi to 1 and phase 0 to 1. So if the bit transmitted is a 1, the carrier phase is a pi, or else if it's a 0, the carrier phase is a 0. It can be the other way also, pi for 0 and 1 for 0, but this should be an agreement in both the transmitter and receiver. If the transmitter is using pi phase for bit 1, then the receiver should also be understanding that way. So this is how the BPSK phases change when this decay comes into the DPSK system. Now coming to the receiver, this carrier phase is arbitrary. So the ultimately the BPSK constellation that will be tilted by an angle theta due to the phase incoherence. Probably you remember the BPSK transmitter I made with USRP and LabVIEW. There in the receiver constellation, you can see there is a tilt in the constellation. This is due to the changes in phase. Now the receiver constellation looks like this. Instead of coming at this point, and you expect an amplitude here. This amplitude is I mark as A because we do not know how much it is, because at the receiver I may be using 1 cos 2 pi FCT. I do not know the amplitude. So together, if you take here, this will be some amplitude here and some amplitude here. You expect it here, but due to the phase incoherence, this is tilted by an angle theta, so that this point this constellation, received constellation, will be a cos theta, a sin theta, and this is a cos theta minus a sin theta. Okay. So this distance is a cos theta, and this is a sin theta. This is the in phase component xi, this is a cos theta, and this is the quadrature component xq. So this is my minus xi and minus xq. So what my receiver sees are the in phase and quadrature components. If you come here, the receiver ultimately measures the coordinate xi0 and xq0. What is this 0? This is the 0 indicate that these are the measurements taken at time t, and another measurement xi1 and xq1 at time 2t. So these two measurements, the receiver makes these two measurements. The 0 indicates the measurement at time t, and the 1 indicates the measurement at time 2t. Why? Because there is a delay in the transmitter by 1 clock duration or 1t. So the decision is ultimately based on this inner product, that is xi0, xi1 plus xq0, xq1. If it is less than 0, a0 is received. If it is greater than 0, a1 is received. So this is 1/4. This I can write a times b is a plus b whole square minus a minus b whole square divided by 4. So that this becomes xi0 plus xi1 whole square minus xi0 minus xi1 whole square divided by 4 plus xq0 plus xq1 whole square minus xq0 minus xq1 whole square divided by 4. If this is less than 0, the received bit is a 0. If it is greater than 0, received bit is a 1. You may even discard this 1/4 because the right side it's a 4, so that I can turn it into 2. Like these two I can combine together. Like I have this equation xi0 plus xi1 whole square plus xq0 plus xq1 whole square minus xq0 minus xq1 whole square minus xi0 minus xi1 whole square. If this is less than 0, the bit received is a 0. If it is greater than 0, the bit received is a 1. So ultimately the decision making is testing whether the point xi0, xq0 is closer to xi1, xq1 or negative of that minus xi1, xq1. So one point is here, this is one point and this is a negative point, minus xi minus xq. So the receiver looks like this. I have the DPSK signal coming here, and it is passed into two channels. So one channel, the dot product is taken with the cos to pi fct, and here it is shifted by 90 degree, and this is assigned to pi fct. And here this dot product is taken with this integral also. So after this integration, you will get one value here that is delayed by 1 unit along one clock cycle or one bit duration here. So that this is an xi1 and this is my xi0, and this may be my quadrature component, this may be my xq1, and the coming through this is a xq1. Okay, so that this relation is established here. This equation is established here. This xi0 xi1 plus xq0 xq1 is realized here. Okay, in this summation. So here you make some decision whether it is greater than or 0 or less than 0, and the bits do go out. This is how the DPSK receiver works. And its probability of error is half e raised to minus EB by n. This derivation is not included in your syllabus, so I don't go into that. It is half e raised to minus EB by n. And when you come to the outcome of this session, you understood the DPSK system, the working of the DPSK transmitter and receiver, and of course the probability of error. Only you have to understand it. And we come to the end of this module. Actually, in this module we understood the digital modulation schemes. Why do we do this? Because we cannot transmit bits through an antenna. Instead we convert them to sinusoids and transmit through an antenna or other communication channels. Now in this we saw the three coherent systems. One is binary phase shift keying, then there is binary one is binary phase shift keying, and the other is quadrature phase shift keying. Quadrature phase shift keying, that is a variation of the BPSK. And we understood the probability of error, the transmitter, receiver, etc. I told you the demos in Python and LabVIEW. Now then we saw the binary phase shift, frequency shift keying system. There also you understood the receiver and transmitter. Then in the end you understood a non-coherent scheme, that is a differential phase shift keying system. So with this the module on modulation or digital modulation is coming to the end. And next we will consider the parts in the second module, that is about the intersymbol interference and signal modeling and all that. So until then, bye bye.